The first section of chapter 9 has a great deal of material in it. So what I'm going to do is I'm going to split this up into two parts, and this is the first of the two parts. I want to think back to Calculus 1, where typically we had functions like f of x equals 3x plus 1. The domain of that function is the collection of all real numbers. You can put any real number x into it and get an answer back. In particular, if you were thinking about some point where x is equal to c, you could make an interval that contains x equals c, and at every point inside that interval, you have a function value. So between any two places where your function is defined, every number between those two places has a function value defined as well. And this is what I mean when I say these kind of functions are defined on a continuum. There is a continuous, unbroken interval where the function is defined. Of course, you can get into complications where you have a removable discontinuity or vertical asymptotes or any sort of that thing. But the nice functions will be defined on intervals, at least in pieces. That's what lets us take limits. If I want to think about the limit of a function as x approaches c, what's required is that for every x close to x equals c, I get a function value back again. The issue of whether or not I get a function value right at x equals c, that's a different topic. We'll talk about that later. But basically, this continuum idea, this is what lets us do limits, that lets us define derivatives, even though we have a big bag of tricks for derivatives. This is where it came from. It lets us define integrals. Basically, everything we've done in calculus up to this point, secretly hidden behind the scenes, is this whole function defined on a continuous interval, a continuum. Now we're going to change that. I want to think some more about the nice functions. When we defined derivatives, I want to know the tangent line at the place on this graph where x is c. What we do is we define a function value at a nearby spot, a place where x is equal to c plus delta x. This fraction is the change in y divided by the change in x. So that's the slope of the straight line that goes between those 2 points. When you take the limit as delta x goes to 0, which is okay to do because this function is defined on a continuum, basically this point slides down the curve and approaches this point, but is never exactly x equals c. And if this limit exists, we call that f prime of c. So this is how we did derivatives in the first place. Notice I have to have a function value for all x's, in this case at c, and close to c. Even something like the graph of the tangent function is, at least in chunks like this, strictly between negative pi over 2 and pi over 2. I have a function value for each x value. For each x strictly between pi over 2 and 3 pi over 2, I have a function value. The only bad spots on this graph are places where x is an odd multiple of pi over 2, which, if I wanted to be fancy about it, I could say, think of n as being an integer, a whole number. Odd whole numbers look like 2 times a number plus 1. Odd numbers are 1 more than an even number. So if I wanted to make a list of all of the places where the tangent is bad, I could just write down this formula, and that would tell me all of them. Aside from these distinct isolated spots, though, the tangent is as nice as the x squared function is. We're going to have a new word. The word sequence is going to mean something very specific to us. A sequence is a function whose inputs are integers. Usually we use integers 1, 2, 3, and so on. Sometimes we start at 0 instead of 1. Sometimes it might be convenient to start some other place, but in any case, a sequence is just a function, except that you're only allowed to put integers into the function. For example, the bad spots on the graph of the tangent function that we just looked at form a sequence of numbers. In general, you could think of it as 2n plus 1 times pi over 2. For this kind of work, usually instead of calling our functions, which are these sequence things, instead of calling them f or g or h or so on, usually we call our sequences a or b or c or some such letter. This isn't an iron rule. You can name a function anything you feel like naming it. Ordinarily, when we speak about function values for a function such as f, we would write f of x, f open parentheses, x close parentheses. Strictly speaking, if we wanted to be consistent about everything, we would then say our sequence outputs are going to be a of n, or b of n, or so on and so forth. That's not what people write, though. They write a with a subscript of n, or b with a subscript of n. You pronounce this a sub n or b sub n. If we want to be picky about it, the function f of x equals x squared for x is 1 or bigger, and the function a of n, which we write as a sub n, equals n squared, where n is an integer that's at least 1. Strictly speaking, these are not the same function because one of them takes inputs that are any number bigger than 1. So you could put x equal to 3.57, for instance. That's not allowed in the sequence function. N has to be a whole number, in this case, bigger than 1. If you draw the graph of the f function, it's a piece of y equals x squared. It's a piece of our usual nice parabola that we like so much. As long as x is bigger than 1, you can take limits, you can do derivatives, you can do all of the usual calculus 1 things that we have previously discussed. But when you look at the sequence function, a sub n equals n squared, that's not so nice. I don't have a curve that connects these dots. I've just got the dots themselves. So if I wanted to try to take limits of this kind of function, say the limit is n approaches 2, it's not going to work for me. I have to be able to get a values for any number sufficiently close to 2, and I can't. I only have an a number at 2. So I can't do limits of things like this in the usual sense of the word, and I certainly can't do derivatives. If I look at this part of the graph and I ask you, what straight line does that look like? Tell me the slope of the straight line, which would be, I suppose, a prime sub 2. That doesn't even make any sense. The graph of the sequence function close to this spot is a single dot. It's not a straight line at all. It doesn't look like a straight line. And there's no reasonable way for me, given the information that's inside this box, to tell you what the tangent line ought to look like. Contrast that with that situation. I have lots of points close to the place where x is 2. I can write down my limit definition. I can figure out the derivative. I can figure out the slope of the tangent line. So there's a fundamental difference between these sequence things and the kind of functions that we've thought about previously. We need to keep that in mind or we'll get tripped up on some details. For these sequence functions, the idea of limit as n approaches 3 of a sub n doesn't make any sense. Neither does limit as n approaches any particular finite number of a sub n. But what we can do is this. We can at least look at the long-term behavior of these a sub n numbers. As I calculate a sub n and I let the n get big, as I allow the n to get larger and larger and larger, either the a sub n numbers that I'm looking at will settle down to some particular number or they won't. When I say limit as n tends to infinity, a sub n equals L, informally that means that by making the n big enough, all a sub n's further down the list resemble L. This is an extremely informal way of putting this. This is where we'll start though. To keep things concrete, I want to look at an example. My a sub n, a number n, a of n, if you want to be picky about it, is going to be 2n plus 1 over 3n plus 2. N has to be a positive integer though, so I can't go sticking n equal 1.5 into this thing. I can put n equal 1, 2, and then getting further down the line, 10, 100, 1000. In each one of these, I'm going to put the value of n into this formula here and see what I get. You can check the arithmetic if you want, but a sub 1 is 0.6, a sub 2 is 0.625, a sub 10 is 0.65625, a sub 100 is 0.665562939. I got these numbers from my calculator. A number 1000 is 0.666555626. It doesn't take a rocket scientist to make a few observations here. We're still being very informal, so when I say it looks like, I mean that. We appear to see a pattern going here. We think we probably know what's going on, but we don't have a hard logical proof or anything. But it looks like as you make the n bigger, the a sub n numbers are getting bigger as well. That appears to be the case. Secondly, it appears that as I make the n really big, the a sub n numbers, the outputs of my functions, they seem to be getting more and more like 2/3. If that second thing turns out to actually be true, which it does, that's what I'm going to mean when I say that the limit as n tends to infinity of 2n plus 1 over 3n plus 2 is 2/3. And again, let me harp on this. Never say that the limit approaches 2/3. The thing that approaches 2/3 are the individual 2n plus 1 over 3n plus 2. The limit is 2/3. It turns out that the way that it looks is actually right. I want to look into that a little bit. The way we're thinking is that as n becomes big, the a sub n gets closer to 2/3. So a perfectly reasonable thing to do would be to look at the difference between a sub n and 2/3. I'll take the absolute value so I won't have to worry about any minus signs. If what we think is right, then whatever this works out to be, a sub n minus 2/3 should tend to 0 as n becomes very large. So we're just going to do some algebra. I'm going to get a common denominator. I'm going to simplify my fraction. And I have -1 upstairs. So when I do the absolute value, all that happens is the minus sign goes away. And see, this is what we want. As n gets real big, 3n plus 2 gets real big. 1 over that gets real close to 0. 1/3 of something that gets close to 0 gets close to 0, and our thinking is right. As you let the n get real big, the distance between an and 2/3 tends to 0, which is what we said we thought. Oh, and I'm going to reuse this example in a while. So this fact that absolute value of an minus 2/3 is 1/3 times 1 over 3n plus 2. I'm going to reuse this fact after a while. When I get there, I'll just say I'm reusing that fact that we figured out previously. I want to point out something that people will typically try to do when they shouldn't. I want to take the limit as n tends to infinity of 2n plus 1 over 3n plus 2. I'll write that as the fraction of the two limits separately. Limit as n tends to infinity of 2n plus 1 divided by the limit as n tends to infinity of 3n plus 2. The top would be plus infinity, and the bottom would also be plus infinity. And presumably infinity divided by infinity is 1. If you believe that, you have to believe that the limit is 1. That's wrong. We just proved that the limit was 2/3. So this doesn't work. The reason that it doesn't work is that business about splitting the limit of a fraction up into the fraction of the limits had strings attached to it, just like the antiderivative trick does. Number one, both limits have to exist. And when I say exist, I don't mean equals plus infinity. I mean actual honest to goodness numbers, and infinity is not a number. Secondly, the one on the bottom isn't 0, which is not an issue here, but that first part is, this limit doesn't exist, even though some people write equals plus infinity. This limit doesn't exist either. The fraction of limit trick does not apply to this problem. But if you do that, you could easily convince yourself that the limit was 1, when in fact it's 2/3. If you want to do this fraction of limit thing, though, you actually can sort of do it. Take the thing you're taking the limit of and factor an n out of the top. So removing a factor of n from 2n leaves you with the 2, and n times 1 over n is 1, so that algebra is correct. Do exactly the same thing on the bottom. When we're taking the limit as x approaches 5 of a function, we are not setting x equal to 5. We're allowing x to become close to 5. When I'm taking the limit as n tends to infinity, I most certainly am not setting n equal to infinity. I'm allowing the n to become very large, but it's still some finite number right up to the moment where the limit has been evaluated. So n in this expression is always an actual whole number, so I can cancel those n's out. There is no logical problem with doing it this way. If the limit of the top exists, which it will, and the limit of the bottom exists, which also does, and the one on the bottom isn't 0, which it won't be, then it's legitimate to split this up into the fraction of the two limits. 2 is a constant, as n tends to infinity, 2 remains 2. 1 over n tends to 0 as n tends to infinity. I didn't say 1 over n equals 0 when n equals infinity, because that doesn't make any sense. The limit of the top is 2 plus 0, which is 2. The limit of the bottom is 3 plus 0, which is 3. And you see we get the right answer doing it this way, because all of the strings attached to this fraction of limit business are obeyed now. You may remember in Calc 1, when you talked about limits, there was an informal discussion, and then there was an extremely picky technical definition involving epsilons and deltas. Likewise, we've had an informal description of what we mean by the limit of a sequence, and now will be official. The statement that limit as n tends to infinity of a sub n equals L, where L is an actual number now, not the infinity symbol or negative infinity, means this: give me an epsilon bigger than 0. Could be big, could be small, but it's positive. Given an epsilon bigger than 0, you can always find an index capital N, which can depend on the epsilon, so that if the index on the a sub n is bigger than that capital N, then the distance between a sub n and L is less than epsilon. This is a fancied up way of saying, by making the index big enough, beyond that index, all of the a sub n's are as close to L as you care to make them in terms of some preset tolerance epsilon. I want to go back to my example before. We think that the limit as n tends to infinity, 2n plus 1 over 3n plus 2 is 2/3. I want to use the limit definition to convince myself of that. What I have to do is I have to look at the distance between a sub n and 2/3 and see if I can guarantee that this is going to be less than some positive number epsilon by making little n bigger than some particular index capital N. So I'm going to have to work with some inequalities here. I have to think about what does it mean for 1 over 3 times 3n plus 2 to be less than epsilon. In an inequality, you can always multiply both sides by a positive number and not mess the inequality up. So multiply by 3, also multiply by 3n plus 2. Simplify the algebra, and you find out that the desired fact is going to happen if 1 is less than 9 epsilon n plus 6 epsilon. That is to say, 9 epsilon n plus 6 epsilon needs to be bigger than 1. I'm trying to figure out how the little n has to act. So I'm getting the part with the little n by itself. 9 epsilon n needs to be bigger than 1 minus 6 times epsilon. And since 9 times epsilon is positive, I can divide through by 9 epsilon. If little n is bigger than 1 minus 6 epsilon over 9 epsilon, the inequality that I want to be true will be true. We're basically done. What we've convinced ourselves is if the index is bigger than this number, which by the way need not be a whole number, but if the index on a sub n is bigger than this, then the inequality absolute value a n minus 2/3 is less than epsilon will be true. So I'm going to let capital N be any positive integer that's bigger than this. It could be a little bit bigger than that number or a lot bigger, I don't care. If little n is bigger than that capital N, then this number is going to be excuse me, then little n being bigger than capital N is this, little n will be bigger than that, and absolute value of an minus 2/3 less than epsilon will be true. So we've actually manufactured the capital N. Let capital N be any positive number that's bigger than that, and you're in business. This says, by the definition, the limit as n tends to infinity of a sub n is 2/3. This is how you would do things with the limit definition. As you can see, it's just as bad as the limit definition was back in Calc 1. As in Calc 1, we're going to need some tricks to help us out here. I'm going to call this the f of x trick version 1 because we'll have several variations on a theme on this. Suppose that you've got a nice function that you would have liked if you were doing Calc 1 again. Also, suppose that when you stick positive numbers into this f function, you get the sequence numbers a sub n out. Also, suppose that the limit as x tends to infinity of f of x is some number L, some actual number. Then I can make a conclusion. I can say the limit as n tends to infinity of a sub n is that same number L. The reason for this is very easy to understand. For the Calc 1 type function, what does the statement limit as x tends to infinity of f of x equal L mean? It means however the function acts early on, if you make the x big enough, then for all sufficiently large x, f of x looks like L. That's all that that statement means. You may or may not be able to make f of x actually equal to L for some x's, but that's irrelevant. Now, if x is big, all f of x's look a great deal like the number L. But amongst those f of x's are f of 1 and f of 2 and f of 3 and f of 8 and so on and so forth. F evaluated at a positive whole number has to start looking a great deal like L if the positive whole number is big enough. But these are function values for the f of x function, and all of those start looking like L after a while. So the reason that this statement that we've made is true is that the whole number function values are just special cases of general function values, and the general function values are all tending to L. So let's use the f of x trick version 1 on our example again. A sub n is going to be 2n plus 1 over 3n plus 2. I want to emphasize this makes sense only when n is 1, 2, 3, and so on. I can't do derivatives of these things, but I can cook up a function that firstly, I can do derivatives of, and secondly, if I stick whole numbers into f of x equals 2x plus 1 over 3x plus 2, then I can take limits of that kind of thing because the f function is defined on a continuum. I want to stop here just for a second. A lot of people looking at this think that it's just kind of a really dumb word game because the thing I'm actually going to look at is this, which is exactly the same thing I want with the n, except the letter n has been replaced with letter x, so it seems like it's just a silly thing to do. But it isn't. If I think that, I've misunderstood the nature of these sequence functions. The sequence has outputs that you can count, 1, 2, 3, 4, and so on, and the f of x doesn't. If you take math reasoning, you'll find out all kinds of interesting stuff about that. But don't fall into the trap that I'm just making up a different letter to call the same thing. The n and the x act fundamentally different from each other. But having said that, I want to look at the limit as x tends to infinity of f of x, polynomial on top, polynomial on the bottom. The one on top tends to plus infinity, and so does the one on the bottom. This is an indeterminate form of type infinity over infinity, which means I can use L'Hopital's rule on it. The derivative of 2x plus 1 is 2 plus 0. The derivative of 3x plus 2 is 3 plus 0. It would be a mistake to do L'Hopital's rule again to it because this isn't an indeterminate form anymore. The top of that fraction is a constant, and so is the bottom. We are taking the limit as x tends to infinity of the constant function 2/3. The limit is 2/3. And then we say, by the f of x trick, the limit that we're after is 2/3. This is what I mean by the f of x trick. As a more complicated example, I want to let a sub n be the square of the natural log of n divided by n, and I want to try to figure out whether this series settles down or converges to something. If you look at the top of the fraction, as n becomes real big, we've already seen I can make natural log as big as I want to make it. The square of that will also be very large. So the top of the fraction tends to infinity. As n gets real big, n gets real big, so does the bottom. I'm going to use the f of x trick on this, where f of x is, as we were saying a minute ago, the same thing as a sub n, except I'm using the letter x instead of n to indicate that I'm on a continuum now. When I write this limit, because it's an indeterminate form of type infinity over infinity, I can do L'Hopital's rule to it. The derivative of the square of something is 2 times the first power of the something times the derivative of the something. So the derivative of natural log of x squared is 2 times natural log x times the derivative of natural log x, which is 1 over x. Meanwhile, on the bottom of the fraction in our L'Hopital calculation, the limit, the derivative of x with respect to x is 1. So after you simplify it a little bit, this is the limit that we're now interested in. Notice the top of the fraction still tends to infinity, and so does the bottom, so I can do L'Hopital's rule on it again. The derivative of natural log x is 1 over x. Derivative of x is 1. So we're looking at the limit as x tends to infinity of 2 divided by x. Again, I'm being picky about this. None of those numbers, 2 over x, are equal to 0. None of them at all. 2 over x is never 0. But as I allow the x to become arbitrarily big, 2 over x gets arbitrarily close to 0. And that's what we mean when we say that the limit is 0. So again, don't ever say that the limit approaches something. That's terrible language. By using the f of x trick, I guarantee you that these numbers all get real close to 0 as you increase the n, and as a result, the limit as n tends to infinity of a sub n is 0. This is mentioned in your textbook, so I thought I'd at least say something about it. If you take a sequence and you know that the limit of the absolute values of the a sub n's is 0, then the limits of the a sub n's themselves have to be 0. Also, if the limit of the a sub n's is 0, then the limit of absolute value of a sub n is also 0. I think these facts are obvious, but in case they're not, let me say just a couple of words about this. Suppose that this is true. What does that mean? That means that the distance between a sub n and 0 can be made as close to 0 as you want by making the n big enough. That means that the a sub n must be close to 0, which tells you this must be true. On the other hand, if the limit of the individual a sub n's tends to 0, and you went off and looked at the distance between a sub n and 0, look at that. Well, that means that has to tend to 0 because the a sub n's have to get close to 0. But if that happens, that means that the individual absolute value of a sub n's must get close to 0 also, and that's the second statement. So if I have a sequence that tends to 0, the absolute value version of the sequence also tends to 0. If the sequence itself has limit 0, then the absolute value version also has limit 0. As I said, I think this is pretty obvious, but I at least wanted to say something about it. Occasionally, this fact will be useful to know. Coming soon in part 2, there's going to be a few more things that are fairly concrete and specific. We're going to have properties of these sequences, which are basically going to be inherited from properties of limits. As in Calc 1, we're going to have a squeeze theorem for these sequence functions. But then we're going to have 3 topics that are kind of abstract-y. We will look at some pretty good examples of each case, but we're going to be having some ideas coming up soon that are on a slightly higher logical level than we've done in the past. We're going to talk about monotone sequences, bounded sequences, and then there's this great fact that has tremendous applications for us. If you have a sequence that is bounded and is also monotone, then that sequence converges to something. It settles down to something. Its limit exists. That fact is going to be very interesting to us because it's of a different character than the things we've done before. That third fact is not going to tell us what the limit is, but it'll tell us that it exists. So we're going to begin doing a little bit more higher level thinking here. I'm going to stop this one right now though, because it's getting too long. I'll try to get part 2 out within the next couple of days. Hope everyone has a good evening. I'll talk to you later.